In this video, we'll take a look at the Kinetic Reactor unit operation in CHEMCAD. We'll talk about the main data entry. We'll talk about the data you need to supply to the reaction module, and we'll work through two examples. One is the Toluene Hydrode-Alkylation system. The other is a reversible formation of methyl acetate from methanol and acetic acid. When we're done with this, you should be able to use the Kinetic Reactor unit operation, and you should be able to convert reaction rate data into the form that the CHEMCAD needs to do the kinetic calculation. In the Kinetic Reactor, you'll specify one or more reactions, including stoichiometry and rate constants. You'll specify what phase the reaction occurs in. You'll specify a key component in a conversion, or you'll specify the reactor volume. You can enter your reaction rate data in different units that are encountered in the flow sheet, and there's also an option to specify the reactor dimensions. We're not going to discuss that in this video. CHEMCAD does its kinetic calculations based on the rate equation you can see here. You can see that in the rate equation, we've got the reaction rate on the left side. We're including the stoichiometric coefficients. We've got a rate constant, K sub j. And you can see in the numerator a product of compositions to powers, which is the form you're used to seeing. The A superscript would be 1 for a first order reaction, 2 for a second order reaction, and so on. We'll talk more about the meaning of those terms in the denominator later. But for the first example, those won't show up at all. So the first example we're going to look at is designing a plug flow reactor for toluene hydrode-alkylation. What you see here is based on example 7.2 from the CEDAR Process and Product Design book. Third edition, I believe the numbers for the fourth edition are substantially the same. The reactor feed is going to be at 1200 degrees Fahrenheit, 494 psia. You'll note that these are English units or American engineering units. I've got my inlet component flows in pound moles per hour. I know my reaction rate constants. The reaction rate constant is assuming that the concentration unit is going to be kilomoles per cubic meter, activation energies in calories per mole, times in seconds. So these don't line up very well at all with the units in the main flow sheet. What we're looking for ultimately is the reactor volume required for an adiabatic plug flow reaction at 75% conversion of toluene. The problem also specifies using Pang-Robinson thermodynamics, so we'll set up the main simulation to use that thermodynamic system. So I've set up a simulation here with the components for the reaction system we're discussing. I've set up the feed stream and an empty kinetic reactor. You can see I've got the 5 components: hydrogen, methane, benzene, toluene, biphenyl already entered. If we take a look at the thermophysical properties, you can also see in the thermodynamic settings, you can see that I've got simulation set to use Pang-Robinson for vapor fugacity calculations. That was the set choice I made manually after the thermodynamics wizard ran. The wizard also selected the UNIFAC method for K values. However, we're not going to have any liquid vapor equilibrium in this problem, so this choice is really not relevant to us here. So I'm going to cancel out of here. And let's set up the reactor. Okay, and in the reactor, I need to set up one equation. I'm going to let it inherit the pressure from the feed stream. I'm not going to worry about pressure drop. I'm going to use the standard kinetic rate expression. My alternative would be to define each reaction separately for each reaction, or I could write Excel Visual Basic to do all the reaction kinetics. We need to specify a reactor type. The problem said do a plug flow reactor. This is a vapor phase reaction, so I'll select vapor only. If I knew I had some liquid present, I would specify vapor reaction mixed phase so that CHEMCAD would look at the vapor liquid equilibrium. However, that mixed phase reaction still would only have reaction occurring in the vapor phase. We'll set the system to operate adiabatically because, again, that was the problem specification. And my initial requirement was to specify the conversion of toluene, and that should be 75%. let's look at the more specifications tab here. I noted previously that the flow sheet itself is in American engineering units, but my rate data are not in American engineering units. So let's take a little bit of a closer look at this reaction and information tab. What we want to make sure of is that we select the correct units for the reaction rate information and that we select a consistent set of units. So for the problem that we're dealing with the given information, I know that my concentrations were supposed to be in kilomoles per cubic meter. So you can see that I've established those here. My concentrations are going to be in moles per unit volume. My activation energy was actually given in calories per mole, but I've already set my mole basis to be kilomoles. So rather than calories per mole, I'll say kilocalories per kilomole. And I also had to set my time base to be in seconds. Let me go ahead and fix these here. This should be in kilomoles per second, in cubic meters, in kilocalories, moles per volume. Just for consistency, I'll move this to kilograms. And now I need to enter the rate information for reaction 1, which is the only reaction I've got. So I'm going to type in the numbers here. My pre-exponential factor is 6.3 times 10 to the 10th. My activation energy is 52,000. Remember, that's kilocalories per kilomole. And then I have, as a reactant, hydrogen. I've got a reactant, toluene. I've got a product, benzene. And I've got a product, methane. So let's put my stoichiometric coefficients in first. Now I need to enter the exponential factors for each component in the system. These are the exponents that go in the rate equation. CHEMCAD makes some guesses about these based on the stoichiometric coefficients. My strong recommendation for you is that you enter these yourself always. So for hydrogen, remember that my reaction was half order with respect to hydrogen. It was first order with respect to toluene, and zero order with respect to benzene and methane. So for the zero order, I'm going to enter 10 to the minus 6 for the order to avoid issues with how CHEMCAD deals with blanks. And now I've entered all that data. I can run the unit operation. And if I look at the streams around it, let's put this in molar units. And you can see that I have converted about 70, or I've converted 75% of the toluene. I've got 25% of it left. So that's how the kinetic reactor module works for this relatively simple problem. Now let's look at a more complicated system, the synthesis of methyl acetate. This is the same system we use to look at the stoichiometric reactor, equilibrium reactor, and Gibbs reactor. In this case, what we're going to do is take an equimolar feed of acetic acid and methyl alcohol, 15,000 pounds an hour feed, 120 degrees Fahrenheit, 5 psig. Now, when you looked at the CHEMCAD kinetic equation previously, you might have noticed that it only has basically a forward reaction. So if you have a reversible reaction, you need to rewrite it as two separate reactions. So for the methyl acetate synthesis, we have the forward reaction, methanol plus acetic acid to make methyl acetate and water. And then we have the reverse reaction, methyl acetate plus water to make methanol plus acetic acid. So I need actually the two rate constants separately. Before we talk about the rate equation in more detail, I'd like to explain something about why those denominator terms appear. So I'm going to look at a couple of standard forms for catalytic reactions. One of them is the Elaideal Kinetics. In this case, what we have is one of our components adsorbing onto the surface, binding with an active site. Then that surface complex reacts with the other reactant to form a product complex with the surface site, and then the product surface complex dissociates to produce a product and returning an active surface site. In this case, what we have is something that is first order with respect to both reactants, but we have these terms in the denominator. These capital Ks are basically equilibrium constants between the solid phase and the fluid phase. So what this denominator term represents is the loss of those surface sites due to adsorption. And I might even have another term here in the denominator for the adsorption of AB onto the surface. If you have some familiarity with bioprocesses, you might recognize this general form of the Elaideal kinetics as being very similar to Michaelis-Menten kinetics, where you have the rate of substrate consumption being proportional to the substrate concentration divided by this term Km plus Cs, which again accounts for, in this case, binding of complexes with enzyme in the system. So this is another case where you would need that denominator term. Another standard kinetic arrangement is Langmuir-Hinshelwood kinetics, where you have each reactant adsorbing on the surface. Then you have a reaction between the surface components to produce the product and returning active sites. In this case, the rate equation looks very much like the Elaideal form, except you'll notice this exponent 2 here in the denominator term. That exponent 2 is in fact that beta term that shows up in the CHEMCAD kinetic equation. For our example situation, I actually found some real kinetic data. And in this paper, they actually fit their results to 4 different distinct models. So I'm going to show you how to enter the data from each of those 4 different models into CHEMCAD. The first one is what they called an ideal solution quasi-homogeneous model. You'll note here that I'm using mole fractions rather than concentrations. But other than that, this works pretty much like conventional reaction kinetics you've seen before. This first term here, the AF exponential minus E over RT, that's really just the forward rate constant in Arrhenius form. And then the product of that that forward rate constant times this A reverse over A forward times this exponential is the reverse rate constant for the system. There's also a non-ideal solution quasi-homogeneous model, and the only difference between this and the ideal solution is that we're using activities instead of using mole fractions. The authors of the paper also put this into the Elaideal form, and again we have the forward rate constant, we have a reverse rate constant, and we have all these denominator terms that are ratioed to the K value for component D, which in this case is water. They also fit their data to the Langmuir-Hinshelwood model, which is also the Langmuir-Hinshelwood-Haugen-Watson model. And you can see that the difference between this and the Elaideal model is just that the value of beta is 2 instead of 1. So from the paper, these are the values of the model parameters. I just transcribed these into Excel and put them up in a form that was more readable. Unfortunately, these don't map very well at all to what CHEMCAD is looking for. But I can work through the bulk density of the catalyst to convert this rate that's in moles per minute per kilogram of catalyst. If I multiply by the bulk density of the catalyst, I get moles per minute per cubic meter of catalyst bed. I've got an activation energy. I can do some multiplication using this forward rate constant and this ratio of rate constants to the bulk density to get a reverse rate constant. And you might remember that the reverse rate constant is just the forward rate constant with this ratio of the A's and this heat of reaction term. So I went ahead and did all those calculations and ended up with the values you see here, which are what we'll put into CHEMCAD as our model parameters. And you can see now I've written each of these in terms of the pre-exponential factor and the activation energy for the forward and reverse reactions, and then the adsorption constants. Now let's implement this reaction system in CHEMCAD. What you see here is a flow sheet. It's the same base flow sheet we used for the other reactor examples. You can see I've got the same components as before: methanol, acetic acid, methyl acetate, water, ethyl acetate, propyl acetate. I'm also using the same thermodynamics as in the previous system. What we need to do now is put in the kinetic parameters. So let's open up the kinetic reactor model, and I'm going to pull up the spreadsheet I used to calculate the model parameters previously. So I've got two reactions, and we'll do the IQH model first. I've got two reactions. We're going to use the standard reaction model in CHEMCAD. I'm not going to worry about trying to control the pressure or the temperature in the reactor. We'll just make it isothermal, use the incoming conditions. Just for fun, initially we'll size the reactor as a CSTR with the liquid phase only reaction. We'll specify conversion. Let's make the conversion of methanol 50%. Now I need to adjust the specifications on this tab because my reaction engineering units are different from my main flow sheet units. I'm still working with a molar-based concentration, but my molar flow should be in gram moles. My time base is going to be in minutes. I'll go ahead and convert the mass for consistency. My volume is in cubic meters rather than cubic feet, and my activation energy is in kilojoules per gram mole. So this gives me a consistent set of units. I can OK out of this and now put in the values for my first reaction, which is going to be the forward reaction of methanol and acetic acid to form methyl acetate and water. The frequency factor for the IQH model, you can see here, is 3.936 times 10 to the 11th. The activation energy is 45.6 in our reaction engineering units. Our composition type is not actually moles per volume, it's actually mole fraction, so I'll go ahead and change that value. Now let me put in the stoichiometric coefficients of -1. Exponential factor is 1 for methanol, it's first order in methanol. For acetic acid, stoichiometric coefficient again is -1. The exponential factor is again 1 for the reaction. We are producing methyl acetate, so its stoichiometric factor is 1, and its exponential factor is 0, and we'll use 1e-6 to avoid issues CHEMCAD sometimes has with zeros and blanks. And same thing, water is one of our products. So that's our first reaction. Second reaction is similar, except it's the reverse reaction. So let me pull my spreadsheet data up again. For the second reaction, the reverse reaction, the pre-exponential factor is 2.339 times 10 to the 10th power. The activation energy is 41.92. Our concentration type is still mole fraction. I'll fix this typo here. Activation energy is 41.92. Okay, in this case, methanol is a product. Acetic acid is a product. The methyl acetate is a reactant, and the water is a reactant. So we'll put their stoichiometric coefficients in. And remember, for this system now, the exponent on the methanol concentration is 10 to the -6. Same thing for acetic acid. Exponent for methyl acetate, and for water are 1. Let's just take a peek back at reaction 1. I made a couple of typos here. I want to make sure I didn't make the same mistakes in the previous screen. So I can back up to that screen, and those numbers all look okay. So we'll step forward here. And now we're ready to run this reaction model. runs without incident. Let's look at our streams in and out. And you can see that I've got, let's put this into a mole fraction basis. So it matches up. And you can see, again, my mole fractions for the reactants are half what I expected them to be. That's exactly the conversion basis. I've sized this kinetic reactor based on the CSTR model. You can see that was specified here. And the reactor volume now is 28.5 cubic feet. That's actually the volume of catalyst we need to make this happen. If we want to do this as a plug flow reactor, all I have to do is change the reactor type. And I'll step through these screens and run the reactor again. And now you can see that the reactor volume is only 11.9 cubic feet. That's a difference we'd expect based on the lower volumes typically required for plug flow versus continuous flow reactors. Now let's take a look at implementing the non-ideal quasi-homogeneous model. We'll again edit our kinetic reactor data. Number of reactions doesn't change. None of these first page parameters change. We're still using the same reaction engineering units. So all we need to do is update the parameters in the individual reaction equations. So for the forward reaction, the pre-exponential factor becomes 9.672 times 10 to the 11. The activation energy becomes 46.91. And we need to change the composition type to activity now. Similarly, for the second reaction, we can change the pre-exponential factor to 3.401 times 10 to the 10th. The composition type is now activity, and the activation energy is 46.58. So let's run this. And what we see is now that the reactor volume is 8.3 cubic feet. Finally, let's implement the Langmuir-Hinshelwood kinetics, the fourth option in that from this paper. So in this case, again, all we need to do is change the data on the individual reaction sheets. 0.592, 10 to the 12th. Activation energy now is 51.88. Still activity terms here. None of the stoichiometric coefficients or exponents change, but the adsorption factors do. So now for methanol, the adsorption factor is 0.110. For acetic acid, the adsorption factor is 0.04. For methyl acetate, the adsorption factor is 0.024. And for water, the adsorption factor is 0.448. And all these are based on activity to the first power. And the other thing is that for Langmuir-Hinshelwood, the beta factor, that exponent on the sum of the denominator terms, is 2. So let's do the reverse reaction now. And I'll just update the pre-exponential factor, 2.049. That's 10 to the 11th. Activation energy is 1.57. Again, all we have to do is update the adsorption factors. For methanol, the adsorption factor is 0.11, 0.04 for acetic acid, methyl acetate 0.024, and finally water 0.448. Make sure to set the beta factor to 2 for the second reaction also, and we should be good to go on this model. So let's run it again. And now what I get is a reactor volume of, again, about 8.3 cubic feet. So the non-ideal models are actually giving us a pretty consistent result, a little bit smaller than what we get with the ideal model. I would, in the final analysis, go with the Langmuir-Hinshelwood result because that's the form that was recommended by the authors of the paper that did the kinetic study. Based on what we've been through today, you should now be able to convert reaction data you find in the literature into the form that's needed for the CHEMCAD kinetic reactor unit operation. And you should be able to use the kinetic reactor unit operation in your projects or other analyses.